Welcome back and good morning. The topic today is a continuation of last week where we started with convolutional neural networks. And that will most likely keep us busy for the session this morning. And after the winter break in the New Year, we will most likely wrap up the course and we will discuss the material about the recurrent neural network, which is also included in the weekly material for this week. Now, just a quick reminder of where you find the material. So you have the main GitHub address of the Erasmus course. And if you scroll down, you find the registrations, the videos from previous lectures. So in the week of December the 12th and December the 13th, we wrapped up our discussions of neural networks. And we looked also at the solution of differential equations using neural networks. That is a pretty, a topic of great interest recently. And you will find many applications of neural networks to the solution of differential equations. The thing we ended with last week was actually a first introduction to convolutional neural networks. And as we discussed last time, convolutional neural networks are extremely popular, and they have, they are the type of deep learning methods which really gave a lot of traction to the whole deep learning environment and the development of deep learning methods. They have been extremely successful in image recognitions, in many other recognition tasks and classification tasks. So let's go back to some of the basics and discuss a little bit more about the basic structure of convolutional neural networks. And then during the day today, we are going to look at how we can actually write our own code for a convolutional neural network. So the material is a material which you will find in session 7 or day 7. And the chapter of Chapter 9 and Chapter 10 of Goodfellow's text give a very good introduction to the field. So let's go back to the Jupyter notebook from this session 7. And this is something you find under day 7. And this is the Jupyter notebook. And we will essentially cover today, we will discuss in more detail convolutional neural networks and how to build our own code. There is also another textbook which is extremely useful if you wish to dive into convolutional neural networks with applications. And in that specific case, the programming environment is based on the library, which has been developed by Facebook, which is, or Meta as it's called now. And this programming environment or library or whatever we might call it is called PyTorch. So convolutional neural networks have been extremely successful in recognizing images. And if you think of let's say a nuclear physics experiment, it's not uncommon that you will have images from detector responses. And then one can train a convolutional neural network to recognize the type of events which we've had in a nuclear physics reactions. So this could be the emission of a proton, it could be emission of an alpha particle or whatever. Or other types of classification tasks which may be important for, let's say, a nuclear physics experiment or a particle physics experiment. Or if you're looking at scans of tumors, this is a very popular application area. And it's widely used in the analysis of scans from patients with potential tumors. And one can easily recognize them based on a huge training set, whether this is a benign tumor, or whether it's a malignant tumor, or whether more research from the pathologist is needed in case the machine learning algorithm is not able to classify properly whether this is a benign or malignant tumor. So convolutional neural networks have had an extreme success, and you will find huge data sets like ImageNet and other ones, which have been used to train the networks on recognition of, let's say, houses, bridges, it could be cars, trucks, or facial recognition algorithms. And these are very, very active research fields. And it represents one of the, how to say, one of the big success of deep learning methods. So a convolutional neural network, as we discussed last week, is based on the mathematical process of convolution. And you can think of it as a way to reduce the dimensionality of the problem. So just to give you the example which we discussed last week, if you have a big image with 200 times 200 pixels, and then we have the classical 3 color channels, RGB, then you would have an image of dimensionality 200 times 200 times 3. So that means that you would have 120,000 bits and pieces of information which you need to store. And if this image is fed in to your standard neural network, and you have a first hidden layer with, let's say, 100 hidden nodes, then the 200 times 200 pixels are transformed obviously into 40,000 input nodes. And then you have to multiply that with a 3 color channel. So you would have 120,000 input nodes. And if you then have 100 hidden nodes in the first hidden layer, then you get the dimensionality of the weight matrix of 120,000 times 100. And if you're training millions of such images, you can quickly see how big the dimensionality becomes. But let's now look at some of the basic operations which are needed when we are setting up a convolutional neural network. So I'm going to switch to the whiteboard, and we're going to look at some examples, and then we're going to go a little bit back and forth between the whiteboard and the slides here. And the slides is obviously the Jupyter Notebook. So let me bring up the whiteboard here. So if we look at the convolutional neural network, the basics of a CNN, or what we might call the basic layout, of a CNN is as follows. So we obviously have the standard input layer, where we have a different set of input nodes. So we have an X, which is input here. So this is our standard input layer. And then if we just have one type of convolutional layer, then this is normally split into 3 parts. One is the convolution itself, and I indicate that one with a W. So we have a matrix W by which we multiply the original matrix and we reduce the dimensionality. So this is the mathematical process of convolution. So I'm just writing that as a conv. Then this produces an output, which we can call for an S here. So it produces a new matrix. Now, when we perform this reduction by the convolutional process, what is normally done is that this is done with many filters so that we produce several reductions of the image. So if your image is a 200 by 200, this could be reduced to something like a 50 times 50 or whatever kind of dimensionality we want to put into the filter. So this W is a filter, which is now, you can think of as a matrix, which is multiplied with the original input matrix, and that reduces the dimensionality. And then there is a new stage where we have a ReLO, and that normally outputs, so it's just a ReLO function which takes the output from the convolutional process and then scales this output by a ReLO activation function. This is then sent into, and this is something which we will discuss pretty soon, a so-called pooling layer or pooling operation. And this is normally called pooling. And this is another way to reduce the dimensionality. And this whole process here is normally called the convolution part. And that consists normally of 3 steps. So there is a filter which acts on the original data. And this filter has parameters. So these parameters are normally trained by the backpropagation algorithm. And then there is a ReLO stage where we then simply new outputs based on the inputs coming from the filtering process. And this is sent into a pooling layer, which performs a further reduction of the dimensionality of the problem. And then this convolution parts can actually be repeated many times. So we can actually put in dots here to indicate that we can have more convolution parts. Or if we just have one convolutional layer, this is normally then flattened. That means that the results from the pooling part is then transformed into a long vector, which is then sent into a fully connected neural network. So that means that you have performed the reduction of the dimensionalities through different filterings. And then this dimensionality reduction is then used in a standard feed-forward neural network where you perform the standard training and you use the backpropagation algorithm to find the optimal weights and biases. So we can now repeat this with more convolution parts. So you can have many such processes, and many of these deep networks, they actually can contain many convolution stages. And then at the end, this feeds into what we simply call a standard feed-forward neural network, or what is normally called the fully connected. So that means that we have all nodes from the input to the outputs are fully connected as we have in a standard feed-forward neural network. So this can be normally a standard feed-forward neural network. So FFNN stands for feed-forward neural network. Now this produces an output. So we just call it output here. And this output is sent into a cost function or loss function. So we have a cost function here, and that receives as input as well the target values. So this is the basic structure of a so-called convolutional neural network. Now, there are some additional parameters which we need to think of when we look at this filtering stage. In the filtering stage, in order to understand a little bit why we have additional parameters, so if we now look at specifically at this specific part here, where we perform the mathematical process of convolution, which I will also come back to a little bit later, because then we are going to look more at the mathematics and how you can perform the convolutional stage in terms of matrix multiplications or matrix vector multiplications, so that we can actually have mathematical operations which are easy to implement. But if we now look at what happens in this convolutional stage, we would now have an output matrix in the convolution. Sorry here. So we have an output from convolution. So this is the first part in the convolutional stage from convolution. And I'm just going to call this a matrix S. And this is normally written as the convolution, the mathematical convolution of a matrix I, or it can be a continuous function. And this is now convoluted with a filter W. This filter is often also called for a K, for a kernel. So you will often see in the literature that this is often also called or labeled with a K for kernel. So mathematically, if some of you have studied image representation, then in imaging, the mathematical process of convolution via, let's say, Fourier transforms has been one of the more widely used methods. Now, let's take a look now at an input. Suppose now our input is a matrix of dimension 3 times 4. So let's just write it like this. And then when we perform this operation of convolution, you will see then why we have to introduce some additional hyperparameters. So let's just look at this as a matrix, which is a 3 by 4. So let me just take that one away and make it a little bit broader. So we have 1, 2, and 3 here. And then I'm just going to put values like A, B, C, and D. And then I have E, and then F, G, an H. So I'm not doing an exercise in showing that I know the alphabet, but this is just a pretty dull example. And then I have a filter here, W or K, which now is a 2x2 filter. So my input is a 3x4 matrix. And then I have a filter which is a 2x2. And this filter now contains some variables. And this is where the training takes place when I deal with neural networks of the convolutional type. So the training, what it is doing then is actually it's trying to find the optimal parameters, W, X, Y, and Z. Often these filters are tailored to specific examples. Now, when I now perform the filtering here, what I'm going to end up with is a new matrix. And this new matrix here, when I now do I with W, that is going to give me the following. And I want to see if I can squeeze this in on the same page here. So this is going to reduce my dimensionality into a matrix which is 2 times 3. So when I now do the filtering, I'm also going to introduce something which is called stride equal to 1. So stride equal to 1 means that I'm going to take this block here, this one, and this is now going to be multiplied with this filter matrix. But then when I say I'm doing stride 1, it means that in my next operation, which will fill in this slot here, then I'm just going to move one step here. And then I'm taking this block, and then I perform the convolutional process with a filter. And then I take the final block here so that I perform that convolution. And then I move down, and then I have this block. And finally, I'm taking this block here, and the last block will be this one multiplied with the elements which we have here. So if we take the first block here, so let's bring in some colors here, and then we take this block here. So that is going to give us as values A of W plus B times X plus E times Y plus F times C. Then we perform the next operation in the mathematical process of filtering. And then I'm going to take this block here. And then that is going to produce B times W plus C times X plus F times Y plus G times C here. Then we continue with this process, and then we end up with so let's just repeat it again. So we will have the next part, which is going to be this one. And then I'm going to have a C times W plus D times X plus G times Y plus H times C. And then I move to the stage below here. I take this block here. And you see that now the way I'm moving is tuned so that I actually can have all the blocks in this matrix being multiplied with the filter matrix. So I will have this one, and then finally I will have this final step here. So let's just fill in the final numbers. So I'm going to have an E times a W plus an F times X plus I times Y plus J times Z. And then the next one is going to be an F times a W plus a G times X plus F times Y plus K times Z. And finally, I have G times W plus H times X plus K times Y plus L times Z here. So that's my new matrix, which I produced by the convolutional process. And in this particular case, I'm having something which is a hyperparameter, which I'm going to call stride. And this stride is equal to 1. So stride equal to 1 means that what I've done now is that I've been moving, when I perform this operation with a 2x2 block, with a 2x2 filter here, I just move one step here in the next operation. So that means that I'm taking the next 2x2 block, and then I go by the next 2x2 block. If I'd had a stride equal to 2, it means that then I would have actually gotten an output which would have been a 2x2 matrix. In that specific case, I would actually have had this block here, and then the next block would have been this one, if stride was equal to 2. Now, unfortunately, in this specific case, when I'm going to down here, I would not have enough matrix elements here. So that would actually have led to an output which would have contained only 2 blocks. Okay, there's one thing I wanted to mention to you. So stride becomes a parameter in the way we perform the filtering. The second thing which we need to note here now is if you look at the output which we have produced, you see now that the corners A, E, and I, and same with all the numbers along the corners, here, the corner values, they appear only once in the final product. So you see that A appears only here, whereas B, which is not at the corner, appears here and here. You see that the value C appears here and here, whereas the value of D, which is at the corner, appears only here. The value of I, which is also one of the corners, appears only here. And the value of L appears only here. So what is common then is to introduce an additional hyperparameter, which is called the padding. So let's just bring that one up. So additional hyperparameter, in addition to stride. This is called padding, T. And in our case, we had a padding P equal to 0 because we didn't include anything here. So the padding parameter, what it actually means is that you would take your original image. So suppose that image looks like this. So I'm just setting this up now, and we are looking at the corners. So we have XX. This is the X stand just for some specific values. So this could be some specific pixels representing an image. And then if we add padding here, what we are simply adding is an additional fictitious layer here. And this additional fictitious layer has no values of 0 here. So we would typically set 0, 0. But that is going to make sure that the corners will appear in more of the slots than we had if we had 0 padding. So in this specific case, we are adding an additional layer outside the image which we have. So this would correspond to a padding equal to 1. So that becomes like a new hyperparameter. So in the previous case, we had no padding. Now let's look at some specific examples here and how we can actually reduce the dimensionality of a specific image. So what we said now is that we have a image, and let us now bring up the parameters here. So we have an original image. And we are going to label that as an n times n. So I'm just going to look at the square cases, and there's only one color channel. So, and then we are going to have a filter. So this is our matrix I. And then we have a filter, which now is an F times F filter. So this defines this object W, or sometimes you will see that defined as a K, which stands for a kernel. And then, so we have a filter now is equal to, we can put up an example where N is a 7x7 image, and then F is a 3x3 filter. This is a pretty common value. So common values for these filters are either 5 or 3. So then we can have a stride equal to 1. And we could have padding P. This is normally written as an S, and padding P equal to 0. And then we can actually find the final output of the matrix, which we end up with. So in that specific case, what we would get then is that the output size, and it's not so difficult to see that this is the case. So the output size is now going to be defined by n minus f divided by the stride value plus 1. So in this specific case, with n equal to 7 and f equal 3 and stride equal 1 and the padding equal to 0, there's actually going to be a value of the padding, which is going to run, and we are just going to put that one with dots here, because in this case, we are taking padding equal to 0. There's actually a 2 times p, the value of the padding. In our case, the padding is equal to 0. Now, for this specific matrix, which we get as an output matrix with a 7x7 image, which is filtered through a 3x3 filter, then we will get an output dimensionality, which is given by a 5x5 image. And now we just put one color channel. If I take n equal to 7 and f equal to 3, and I have the stride equal to 2 and still padding equal to 0, that is going to give me a reduced image, which is equal to a 3x3. And then we can continue like this. So typically in a convolutional neural network, you're going to produce many such images through every filtering stage. So just let me give you an example here, a further example. So suppose we start with an input matrix with 3 color channels, input image, which is represented by a matrix. And actually, this is a tensor because it's a 3-dimensional object. 32 times 32 times 5. Sorry, times 3. So this is the input image. Now, what I could produce now is 10 outputs. So every convolutional stage does not need to produce only one image, but it could actually produce several images. And then these are scaled continuously. And then at the end, these inputs or these outputs from the convolutional stage are sent into a classical feed-forward neural network. So we could now assume that we produce 10 outputs from convolution. You can produce one, or you can produce more. And then we have a 5 times 5 filters. So what we're doing now is that actually we are producing copies of the image. So we have 5 times 5 filters, and then we could take with stride equal to 1. So that means that, and we have padding equal to 0. So then what we have then is a 32 minus 5 divided by 1 plus 1. So that means that what I get then is a 28 times them. So the dimension of the image gives us a 28 times 28 times 3. So we have 3 color channels. And the what I need then to take into account is actually the number of color channels. So I produce images. So I produce 10 images of dimension 28 times 28, and then plus the 3 color channels times the 3 color channels. So the filter then, when we produce these operations here, then the filter has the following number of parameters, as in total 5 times 5, and then multiplied by 3 plus 1. And that is equal to, because we have the hyperparameter for stride, which is 1 here. So that has 76 parameters. And since I'm performing this process here now for 10 images, that means that with 10 images, I end up with 760 parameters to be trained. And these are normally trained by the standard backpropagation algorithm. So in summary, if I look at a specific type of image, what we have then is that the typical image which we are putting in here, so the typical sizes which we end up with. So we have the input now, which has a width. So I'm labeling that with a 1 here to input to indicate that this is my original image. So this is the width of the image in pixels. And then I have a height, again in pixels. And then I have a D1 here, which is the depth. And that depth represents the number of color channels. And then I need also an additional set of hyperparameters. So I'm getting new parameters, hyperparameters. So we'll have a hyperparameter which I'm going to call K, which will be the number of filters. I'm going to have F, which is their spatial extent. So in the previous case, we looked at a filter which was 5 by 5 or 3 by 3. We are going to have S, which is the stride when we perform the convolutional process. And then this padding, which is also a parameter which is typically used. And the typical values for the padding are either 0 or 1. So that means that this produces an output, which is given by the height times the weight, the width times the depth. And we have an expression for these different parameters. So we can actually set up the width and the height and also the depth of it in the following way. So we would then have a W2 here, which is typically W1. Normally these images can be square images. So minus F. So the filter is normally assumed to be a square filter. And plus 2p divided by the stride plus 1. I have this height, which is equal to h1 minus f plus 2p and divided by the stride plus 1. And this depth 2 is actually equal to k, which is the number of filters which we are producing now. And what we get then, we get then something which is f times d1. This is the filter size, weights per filter. So this is d1. And k so-called bias values, which are trained by backpropagation. And k values, which are all trained by backpropagation. By backpropagation. So the backpropagation algorithm is something which pops up everywhere. And k, this value of k is often chosen in terms of, or in powers of 2. So that's a pretty common choice here. And when we perform this filtering, there are some kind of settings which are used pretty widely. So common settings which you may encounter in the literature. This could be now F, a filter which is a 3x3 filter, and you have S equal to 1, and you have padding equal to 1. Another type of filter which is pretty common to use is F equal to 5. You have a stride equal to 2 and padding equal to 2. And alternatively, an F equal to 5, and then a stride equal to 2, and then you can see a padding equals 0 or 1 or 2. So what you would run then when you're setting up a convolutional neural network is actually a filtering where you would try different sizes of the filters, and you would also try different strides and different padding parameters. Now, one thing which you should keep in mind now is that often these filters, they are really tailored to the specific problem. So there is a lot of experience which people have gained through using filters like those which you would have if you perform a Fourier transform. So people who deal with convolutional neural networks and imaging in particular, they are often people who have a strong training from standard imaging theory, where you would find filters based on Fourier transformations or similar mathematical operations. So this was a little bit about the basics of this type of setup. Now, if we now go back to the typical convolutional part, and we are going to set that one up before we go back to the Jupyter notebook. So the typical setting, or the typical convolutional part, and keep in mind now that the typical convolutional part can produce copies of the image, and that you can have many such types of convolutional parts. So the typical one is one or several convolutions. And when we, after the break, when we go back to the Jupyter notebook, we will look at what these convolutions look like. So on several convolutions in parallel, so that you can produce more than just one image in order to produce one or just a set of linear results, which are then fed into an activation part in order to produce several or just one or one only copies or reduced copies. So these are reduced ones of the original input. Now, after that one, then you produce an output from the convolutional stage, and these outputs are then fed into these linear activation functions, which then also produce its own output. So that is normally done by passing through a ReLU stage. So this is an activation function. So it's a linear activation function. And we discussed this type of activation functions in connection with neural network. And the inputs then are just sent through these activation functions. And that ReLU stage then feeds into the next stage, which is normally called the pooling stage. And the pooling stage, in order to show you an example of what the pooling stage can be, there is one typical example, which is called max pooling. Pooling example. This is the most used one. So you also have to define the connectivity between different nodes. So suppose now that the ReLU, so suppose we have 4 nodes here. So this is the ReLU stage. And this ReLU stage has produced an output of 0.1, an output of 1, an output of 0.2, and an output of 0.1. So this is just an example. Now, this is then sent into the pooling stage. So let's now put 4 nodes here. And what is often common to have in the convolutional stage is that these different nodes are not fully connected. So think back to a neural network. In a neural network, then these nodes here would be fully connected to one of these nodes from the Relo stage. So that means that this node here would connect here, 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 and here, and same with the other nodes. This is the case which we normally have seen for the feed-forward neural network, where we have a full connectivity, and then we simply perform these different affine transformations. Now, with a pooling stage in a convolutional neural network, we have normally what is called sparse connectivity. So let me just put that one up here. So we would have a sparse connectivity. You can actually include that one in a neural network as well. Connectivity. So what you would have now is that this node here connects only with some few nodes. So the node with 1 connects only with 3 nodes in the pooling stage. And similarly here, so this is connected only through to the nearest output nodes. So what happens then is that in the max pooling stage, what we end up with is to compare the different inputs. So if you look at the inputs to this specific node, this receives 0.1 and 1, but it sends out only the largest value, 1. The same if we look at this case here, that receives 0.1, 0.2, and 1, but that produces only 1 as an output. And it's easy to see now that this node also produces 1, and the final one here produces 0.2. So we're just picking the largest value. Now, what is common now with the pooling stage is that we reduce the dimensionality further. Since you now have 3 of the output nodes which produce 1, then the dimensionality is just reduced to 1 of them. So that means that since these are equal in value, then there is no point in carrying on the information from all 3, but you just produce information from 1 of them. So that means that what is sent further is just a 1 and a 0.2 here. So this is a further dimensionality reduction of the problem. So the pooling stage is something which you can see as a dimensionality reduction. And there are no parameters to train. So no parameters. In pooling stage, except obviously the hyperparameters you have decided to how many nodes should be connected. But normally there are no parameters in pooling stage which gets trained because these are preset by you when you start the calculations. And there are no parameters in the Relo stage. There are parameters in the Relo stage, but they are not trained by the network. They are set by you before you start the calculations. So there are no parameters, so we should put a quotation mark here because these are parameters which you fix before the calculation starts. And no parameters in Relo stage. In the sense that when I say no parameters, that means that they do not enter the training which we have, means do not enter training stage. But it's clear that these are parameters which you would need to set before you start running the calculations. So we do not enter training stage. And the training stage, that means that what we have in the training stage are the weights and eventually biases, which are included in the standard convolutional stage. There are no parameters in the Relo stage except those which define the Relo function. And similarly, in the pooling stage, what we have then, whether we define max pooling, which is the most common choice, so we pick only the max values, we also need to define how these different nodes are connected here. So here we would have a connectivity of 3. So one input node connects to only 3 nodes in the pooling layer, but we could define that it should connect to more nodes or less nodes. So these are all things which need to be defined when you're setting up your neural network for convolution. So after the break, we are going to look a little bit more at the mathematics on the convolutional stage. so that you see more clearly how you can represent these operations by efficient matrix vector multiplications. And the matrices which typically pop up then are the so-called tuplets matrices, which we mentioned last week. And then after we've done that, we know basically how to set up a convolution neural network. We are going to look at examples on how we can perform calculations with either using TensorFlow or even setting up our own code for that. So after the break, we are going to look in more detail how to set up a convolution neural network. Welcome back. So let's quickly recapitulate the basic structure of a convolutional neural network. So in summary, in its simplest form, it contains a convolutional stage, which then, if you think of this convolutional stage, there is a convolution, there is a ReLU stage, and there is a pooling stage. And then we have a FC stage, which is a fully connected neural network. And they are by far the most popular ways of setting up a convolutional neural network. And a convolutional neural network can then contain several convolutional stages, where the convolutional stages contain the filtering or convolution, the ReLU stage, and then the pooling stage. And each layer or each stage then may have or not have parameters. So if we think of the convolutional stage where we have a filter, then the filter itself has a set of parameters. And then we have the feed forward part or the fully connected part, which is just normally a standard neural network. That has also parameters which are trained by backpropagation. And then the ReLU stage and the pooling stage, they don't have parameters which are trained in the training stage. But keep in mind that they do have parameters in the definition of the activation function and in the definition of how many nodes we want to connect in the pooling stage. And each layer may or may not have additional hyperparameters. So the pooling stage has hyperparameters, and these hyperparameters are the number of nodes which are connected. The convolutional stage has hyperparameters like the stride and the padding. And similarly, the fully connected one can have hyperparameters when we are training with an additional shrinkage parameter like we've had in ridge regression or lasso regression. And then the ReLU stage does not have, except that the ReLU function itself may have a parameter in the definition of the activation function. So if we now look at the convolution again, and this is something which we looked at last time. So the mathematics of convolution is actually defined by this specific process in case the weights are continuous variables and the x's are continuous variables. That produces a continuous output, which is now filtered away. And the example which we discussed last time could be a set of measurements, x of a, which are done over time. And then these measurements can be pretty noisy. And then we have a filter, which then filters away the noisy part, if we can do that. So this is just an example on how the mathematical process of convolution is set up. So it's defined by this mathematical operation here, and that is normally rewritten in terms of x asterisk w as a function of time, if time is a variable we are looking at. And then we have a discretized version, which simply runs from a equal minus infinity to a equal infinity. And then we have discrete sets of variables a here. And the inverse process is called deconvolution. And one of the examples which we looked at last time, and we've already met that one when we did the, in the project one, the type of function we are looking at there. So we have a mathematical multiplication between two polynomials, and that leads to a new polynomial here, which now contains this delta 0, delta 1, delta 2, etc. And this is something which we could rewrite, and we went through that last time, either in terms of the convolution here as a discrete set of operation, or in terms of the double sum here. So this is the parameters delta are the parameters which result from the polynomial multiplication. And we know what these values should look like when we perform the polynomial multiplication. And when you look at these definitions here, these are something which this is something which we can rewrite in terms of a convolutional operation here. There's a more efficient way of doing that, and that is to set this up as a matrix times a vector. Alternatively, we can rewrite that in terms of a matrix which contains beta and multiplied with a vector which contains alpha here. And this way of doing it is actually the way by which we would implement it computationally and numerically in a convolutional neural network. So when you look at these operations here, if we scroll down, this is something which you can rewrite in terms of a matrix A. And if you look at the matrix you end up here, you see that you have along this diagonal, not diagonals, but different types of diagonals, you get a same value, beta 0, beta 1, beta 2, and beta 3. And that type of matrix is normally called a Toeplitz matrix. And it has elements AI equal to AI plus 1, J plus 1. And that is a typical example. It does not need to be a square matrix. And this Toeplitz matrix is also closely connected with Fourier series. So the kind of insight which people have from Fourier series is actually what has been used in the design of the mathematical operation of convolution in a neural network as well, or deep learning methods. So if we scroll down and pass this repetition of standard Fourier transformations, so I'm not going to go through that. That is just another example of the mathematical process of convolution, and I just invite you to take a look at it. So if we now look at the objects which we have, typically the output can be written out in terms of the input here, and then we have this K, which is a filter or kernel, or something which we denoted by W. So you will often see in the literature that this K can be written as a W or just as a K, K for kernel or filter. And then we would use either K or W as a symbol. And this process is also commutative, which means that we can rewrite this equation in terms of the inverse operation here. Normally, this one is more straightforward to implement in a machine learning library, since there's less variation in the range of the values of M and N. So these are typical things which you can think of when you're setting up your own code for a convolutional network. And many libraries, many deep learning libraries, they implement something which is called a cross correlation instead of convolutional, although it's often referred to as a convolution. And this is a typical operation which is then set up. Now, if we now go on here, just to quickly remind you of some of the dimensionality problems which you face when you're dealing with images, is that if you were to run this through a standard neural network, you would actually end up with huge dimensionalities. And you can think of that in case you have an input vector which has length d 10 to the 6th, and then you construct a standard neural network with one hidden layer, and which has only 10 to the 4th nodes. This means that you will have a weight matrix with 10 to the 4th times 10 to the 6th. That means 10 to the 10th weights to be determined. And since you have 10 to the 4th nodes, it means that you have 10 to the 4th biases. So the number of parameters in that case easily blows up here. And you can simply see that if you then assume that you have an output layer, which is meant to train whether if this represents a sequence of sounds or something else, you need to, and if you then have only one output node, but since the output node connects to 10 to the 4th nodes in the hidden layer, there are in total 10 to the 4th weights to be determined for the output layer, plus one bias. So in total then, you would have something like 10 to the 10th parameters to train. And this is one of the reasons why convolutional neural networks are so popular, because it allows you to actually reduce the dimensionality a lot. So if we just scroll down and look at the way we can represent this in terms of a matrix vector multiplication, one way to look at this is to think of your input now in terms of a 3 by 3 matrix. So this could be your image. So 3 pixels and 1 color channel. So width 3, height 3, and just 1 color channel. And then we have a 2x2 filter, which is then given by the following matrices here. So if we now have a stride equal to 1, which is one of the more common use types of strides, then if you do the math here, you will see that this is going to give you a matrix which is going to be a 2x2 matrix. So if I perform the convolutional operation, this is what I would get when I perform convolution on that matrix. So that means that we set a stride equal to 1. That means that we would start with the element 0, 0, and the filter will act on 2x2 submatrices each time. So that means that the first submatrix it would act on would be these 2x2 blocks, which we have here. And then it starts with a stride equal 1. It starts with this block again, and then includes this one, or actually the 2 first ones, and then I11 and I12. And then in the next case, we would have the lower subblock here. It seems that my pointer here doesn't allow me to highlight all of them properly. But I will start then with when I was stride equal 1. I've done with the first blocks, the upper ones, and then I move down, and then I have the 2x2 subblocks here, this one, and then I would start with I11 and have the next subblock. So that means that when I perform the filtering, this is the output which I'm going to get. This is a 2x2 matrix. However, what is normally done, if we follow that example with polynomial multiplication, is that these operation is normally rewritten in terms of a matrix vector multiplication by defining a new vector where we flatten out the inputs as a vector of length 9. Since we had a 3x3 matrix, we can always flatten that out as a vector of length 9, which looks like this. And then we could have a matrix and a matrix W with dimension 4 times n. And then we get so we have a new weight matrix which looks like this. So if we perform the multiplication of W prime with I prime, this is the same with as above with a convolution with stride equal to 1. That is going to give us the same output as we had before. Because you see that we have a vector of length, actually it's going to give us a vector of length 4. So we had previously a matrix of dimensionality 2 times 2. If we perform this now, we have a vector of length 9 times 1, and then we multiply that one with a matrix of length of dimensionality 4 times 9 times a vector of length 9 times 1 gives us then a vector of length 4 times 1 instead of the original one, which was a 2x2 matrix. So these are typical ways by which you would set up the filtering as an efficient matrix vector multiplication. This is the more common strategy which is being adopted in most of the code. So what you will find here is just a repeat of what we discussed before the break and how we do the pooling and how we actually set up the different dimensionalities using padding and unit strides. You can have 0 padding unit strides. You can have different types of padding and different types of strides. So you will see several examples here on how you can set that up and what kind of output you would get. So one of the things I wanted to discuss now with you is how you can set up your own neural network with a convolution and different pooling layers and different ReLU layers, etc., etc. And the way we are going to do that is the first one is actually by setting up a code using Keras, which is an API on top of TensorFlow. And that's normally what I would recommend if you are going to use convolution neural networks. This is very, very much tailored to basically all kinds of applications, and it's very flexible. Alternatively, if you're familiar with PyTorch, I would strongly recommend using PyTorch. So PyTorch is also easy to parallelize. It's easy to use GPUs if you have access to GPUs, etc., etc. So you can choose whether you want to use PyTorch or TensorFlow, and TensorFlow with Keras as an interface. In the examples here, for the sake of simplicity, I've been using TensorFlow with Keras. And typically, what you need to define then is the input matrix, which you would have. So you would typically have a number of inputs. You would have the pixel width, pixel height, and then the depth. So if you think of these handwritten numbers, which is a classical example you encounter essentially in all machine learning textbooks. In a certain sense, this is a kind of boring example because you see it everywhere. But in the original MNIST data case, what you had, or what you have, are images of dimensionality 28 times 28, and you have only one color channel. So that means that if you think of the input, you would then need 724 input nodes, and that leads to 724 weights to each neuron in the first hidden layer. So if you were to analyze images of the dimensionality 128 times 128, that would require 16,000 roughly weights to each neuron. And if you have 100 neurons, that means 1.6 million weights to train. And then if you add the color channels, then clearly that gives you even higher dimensionalities. So the typical setup now, if you look at the MNIST dataset, so this is the MNIST dataset, which I'm just loading. So scikit-learn has these different datasets, and you can see now that I'm loading these digits. This is a stripped version of the original 28 times 28 images. It's actually only 8 times 8 images, and it has only depth equal to 1. So these are handwritten numbers. And you can see now that the total inputs are given by the number of inputs, which are close to 1,800 images. And then I'm going to split this in train and test when I'm going to run the training. So I'm going to take 80% of these numbers and split that in a training set. And then I will have a test set, which I apply the trained network to. And this has 8 pixels width, 8 pixels height, and just one color channel. And this gives me, it has 1797 inputs. And then I'm setting up my neural network with Keras. And in this case, I'm just setting up the different input layers, the sequential part of it, the fact that it's going to be a dense neural network. I set up the optimizers, the type of regularizers, and then the kind of output, which is going to be a categorical. I have more than a binary case, so I have several categories I want to train. And then I do my train test splitting, as you can see here. And when I run that one, I will have a split into 80% with data which is set to training and 20% to test. And then when I'm creating my neural network now, what I'm using is actually the convolutional neural network layers. So I have a 2-dimensional convolutional layers. I define the number of fields. I define the input shape. I define the type of activation function I want to have, the kernel, the regularizer, so I use an L2 regularizer. I define the pooling layers, so I define the number of connectivities, and then I flatten it out, and then I have my connected neurons. So this is a standard neural network, and that produces, it runs through an activation function of the ReLO type. It has a regularizer, or the shrinkage term, which is an L2 norm. And then I have my output layer, the final one, where I just have the softmax function, which is then used to for the classifications of the 10 different categories, which in our case are the 10 handwritten numbers from 0 to 9. And then finally, I define the type of output and the loss function, which is now defined by the cross entropy. I define the optimizers, which is a stochastic gradient descent. I set up the number of epochs which I want to have, and batch sizes, the receptive fields, the number of filters, the connected neurons, and the categories which I have. And then I have the final hyperparameters, learning rates, and the lambda values, which are the hyperparameters, and then the learning rates, which span from in a log scale from 10 to the minus 5 here to 10 to the first. And then I have 7 values. And then I run through it, I train it, and then I produce my score, which is then simply the standard accuracy, which I'm going to calculate. And in this case here, you can see now the runs. And one of the things you will notice is that this training here doesn't fare much better than what we had previously with a standard feed-forward neural network. And that has also to do with the fact that the number of images which we have are not that many. So if I just scroll down here, you can just go down a little bit. I have a final visualization here where you now can see the final output. If we now look at it here. So let me just bring it up. You see now that in the training, it is doing roughly as well as we had with the feed-forward neural network. And you will see now that they have a region for the learning rate parameter, which is now 10 to the minus 2. So 10, so this is 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2, and 10 to the minus 1. So for these values of the learning rate, we seem to get a pretty good training because they have 100% correctly classified results. And similarly, when we then went down to the test case, we see that we have a test here where we actually have 99% hit. So as I said, when we looked at neural networks, this is the 98% is roughly what humans are able to classify correctly these images. And you see now that the neural network does a little bit better than humans do. If 98% is the average human, training score. So in essence, what we have done here is actually to build a more complicated network than we had with the standard feed-forward neural network. But the result is basically the same here. Now, there are other examples which I put up here. One is this famous data set, which contains 60,000 color images in 10 classes with roughly 6,000 images in each class. And then the data set is typically divided into 50,000 training images and 10,000 testing images. And the classes are mutually exclusive, and there is actually no overlap between them. And you can see that when you look at the outputs here, because these are the quality of the images, you will see now that these are actually mutually exclusive ones because you have horses, birds, frogs. You don't see that well here because these images are a little bit blurred. So you're not training on high quality images. And I think the images here, I don't remember exactly what was the size of the images, but I think these have been scaled down to something like 28 times 28 because you see now that the images are actually pretty blurred here. So when you're setting up the model here, you can then set up in the code here, we can then set up different convolutional layers. So you can see now that they can perform one convolution here. So 6 lines of code below, which you see here, define the convolutional base using a common pattern. So you have a kind of stack of convolutional and then max pooling layers. So I'm performing a convolutional stage here with an activation function, a reload. And then I have a max pooling stage, and then I do the convolution again, max pooling, and then convolution. So you can actually set these convolutional stages as you want. And the thing which is nice here, it tells you also the number of parameters you have and the output shape. And you can see here by these different convolutions which you've set up, you get different types of outputs. And at the end, you've actually reduced down the image to a 4x4 here. And in each stage here, you have a set of parameters which need to be trained. So in total, for this specific case, there are 56,000 parameters which are being trained. And you have non-trainable parameters, there are none here. So the output of every convolutional and max pooling layer is a three-dimensional tensor of shape, height, width, and the number of color channels. And the width and height dimensions tend to shrink as you go deeper in the network. And you see that here because you start with a 30 by 30, and then you go down to 15 by 15, and then 13 by 13. With a pooling layer, you have go down to 6 by 6, and then you have a final convolution here, where the final output shape is a 4 by 4 here. And you can add dense layers on top of it. So you would flatten out the result. And then I have a dense layer here. So I have these 64 outputs, which I have. I define an activation function ReLo, and then I perform my training on the model here. So I actually didn't run through this because this takes a little bit more time. And I see that there's a small typo here. And that is why it didn't run properly. But this is normally something which takes actually a lot of time here. So when I now perform the whole process, where I've done all the convolutions, and then I do my dense neural network. So I have two layers here. One which is the hidden layer, and then I have the output layer, which has 10 outputs, because these are the categories which I have. And then I end up with a total number of parameters which need to be trained of 122,000. So this is actually something which will take a little bit more time. I then use Adam as the optimizer, and then I take the accuracy again as my measure for the successfulness of the model. And then we can finally run it here when I make the final plot here. And in this particular case, you will see that the output which I get is not that good. So this is running through the different epochs, and it's going to take a little bit time here. Now, what follows down here is actually us building up our own feed-forward neural network. So what I'm presenting here, in addition to you setting up everything with Keras and TensorFlow, you can actually develop your own convolutional neural network code. And this is a Python example, and this is actually built from scratch. So it contains different layer classes. So you would have a convolutional 2D layer. There is a pooling 2D layer. There's a flattened layer. You can have a fully connected layer, and then the output layer, which can be added to the CNN object using the interface of the CNN class. And that allows you to easily construct your own CNN, as well as allowing you to get used to an interface similar to that of TensorFlow, which is actually used in many, many real-world applications. So nowadays, what you will see is that TensorFlow/Keras and PyTorch are the typical softwares of choice, which people tend to use in this type of deep learning algorithms. So what you will see here, when you look at the setup of the code, is a list of schedulers, which you have, the way you actually update the learning rate. And this is the same as the functions which we had in connection with a neural network. I have reused the activation functions. I have reused the cost functions. And then what comes next is actually the convolution itself, the type of filters we can set up, and then the type of layers we can set up. And then finally, there's a CNN here where we bring everything together. So you will then, if you scroll through here, you will see how you can actually set this up. So the first class here is actually the one which contains different ways by which you can update the learning rate. And this is something which we discussed a little bit early in the semester. So we can have just a constant learning rate, which is a brute force gradient descent. You can add momentum. You can do adaptive gradient with momentum. You can do root mean square propagation and Adam schedulers. So these are all described below here. And there is also a description, so I'm not going to go through it, but you can take a look at it in case you want to build up your own code for either a standard feed-forward neural network or if you want to write your own code for a convolutional neural network, which is normally a little bit more time consuming. So these are the different schedulers which you can set up in order to update the learning rates. And there are some small examples here. I'm not going to run these codes because it's not that important, but I just wanted to show you how you can actually build up the different elements, and that these elements are elements which you would typically reuse with a standard feed-forward neural network as well. So the next part which comes here are different types of cost functions. So one of the standard cost functions which you may have seen before is actually the standard mean squared error. There is the log reg function. There's a cross entropy. You can keep adding more functions to this. As you can see, this is just a class which we have defined, where we define the different types of cost functions here. You can define activation functions. So you can have the identity where the input to a given layer is equal to the output from that specific layer. And that would typically be used in the output layer when you're dealing with a regression type of problem, when you want to fit and continuous functions. There's a sigmoid, there's a softmax function, there's a ReLU, the linear ReLU, and then the derivatives of these functions. But you have, keep in mind that there are tons of other types of activation functions. And here's an example of how you can use these activation functions. Then we come to the convolutional stage itself. And the way this is done is in terms of these efficient matrix vector multiplications. And you will see the different processes described down here. So if you have how the 2D convolution works in practice, suppose you have an image of dimension 6 times 6, and then you have a kernel, a 3x3 kernel, which looks like this. And this one is a filter, which is then applied to this matrix here. Then when you perform the convolutional process, this is actually what you end up with here. By taking the matrix with a filter, and then you can set up the final convolutional process here, where you get now an output, which is a 4x4 output here. So this is just a typical example on what is actually included in the codes below here. You can then add strides, and so this one actually disappeared here. I have to correct this one. So there are definitions of padding, as we discussed. We have the convolution itself here, and then these are the different processes which we have. So it takes the original image, and then it defines a kernel here, and then it just produces the final convoluted output. So this is just a simple implementation of what we discussed in the previous lecture and also in the beginning of this lecture. So this is the mathematical operation of convolution itself. And then when you now proceed here, then there are examples of where you can take a real image and first a Gaussian low-pass filter, which is also something which is really common to use, and then how that filters out the specific image here. So I'm not going to go into all these details, and just invite you to take a look at the codes here in case you would like to build your own program. If not, the easiest way, in particular if you want to use convolutional neural network for the final project, is actually to go back. So if we go up here again and look at what we have with Keras and TensorFlow. So I just wanted to add these examples here to show you how you can write your own convolutional neural network code. But typically what you would do then, if you now add and include TensorFlow with Keras as an API, you would define the convolutional layers, the pooling layers, and you can make this more and more complicated. And then you can define the size of the filters, whether it's a 3x3 filter, whether it's a 2x2 filter or 5x5 filter, etc., etc. And then you can also, in the pooling stage, you can define how many nodes are connected and what is whether you have a sparse connectivity or less sparse. this is all up to you to define these parameters. And if you're a little bit in doubt, just take a look at the Keras manual, which is actually pretty well written. And that gives you finally the number of parameters you would have for the convolutional stage. And then you would, at the end, you would just flatten this out with a standard feed-forward neural network with an activation function of this Rayleigh type. And then you have the final output layer, which now contains just 10 outputs, which are the handwritten, or not the handwritten numbers, but in this case, the classes you are going to classify here, because you have 10 classes of objects. And as you saw from the images, you could have cars, you could have animals, etc. And there are 10 different categories here. And this gives you the number of parameters, and then you can train the model. And then when you run through the training here, so this should be done now, we can finally evaluate the model. And what you would see then is something which looks like this. So you have an accuracy on the test data, which is 72%, which is actually not that impressive. So this is the validation accuracy, and then you have the final accuracy on the test result. And that increases as a function of number of epochs here. So we are getting close to an 80% accuracy in this case. Now, what I wanted to give you here was actually a tour of and the basics of convolutional neural networks, so that you understand what is being implemented and what the different parameters actually mean. So for the final part of the course now, since this is going to be our first lecture, our last lecture before we take a break, I would like to use the middle of January, roughly around the 15, 16, 17, I sent you a message where I proposed that we could meet on the 17th and the 18th. The 17th, I wanted to bring back some of this stuff and end the whole series of lectures by discussing recurrent neural networks. So these are also included in this set of lecture notes, which you're seeing now, this Jupyter book. And then I also wanted to spend some time where we can discuss the final project. And it's possible to bring together project 1 and project 2 if you want to. And I sent you some examples of what people did last year. So this is fully possible. Or if you just want to make 2 separate projects, 1 and 2, that is also fully possible. So all in all, what I wanted to do now is to simply point to what we could do in the beginning of January. And then I would like to propose that we have a deadline which can be very flexible till roughly the middle of February. The only hard deadline which we have is that the administration wants the grades by the end of February, so that you can get your final grades and then move on to your master thesis, so that we have everything done by, so if you're sending me in the final projects around the 15th of February till the 20th, that gives me time to go through them and also grade them. And then we should be set with the final grades for your 3 first semesters by the end of February. And that should be in due time before you move to your final destination. So I'm going to stop here with the lectures.